session. The first speaker is Professor Vassili Kolokoltsov from the University of Warwick, and he will speak on fractional forward-backward system of Banach-space valued Hamilton-Jacobi-Bellman and Mc-Kean-Vlasov equations arising in fractional mean field games. So the floor is yours.
Okay, thank you very much. So that's really what I'm going to speak about. Yeah, I suppose the title is somehow saying exactly. So the main point, those who working a bit with mean field games, they know that the main object there for study are this forward-backward system. So forward Mc-Kean-Vlasov, backward Hamilton-Jacobi, they are coupled through the control. So here what is proposed here is to extend this to the fractional calculus. So we'll have this forward-backward system, forward fractional now Mc-Kean-Vlasov, backward fractional Hamilton-Jacobi equation. And so how we can build the solution, of course, well-posedness, and in rather I would say reasonable generality, which includes also systems on the manifold. So this is the main point of the talk. So this is bibliography. My talk is based on the joint work with Mariana Troeva, who is here. So this is first two papers, which somehow starting this topic. So let me stress that these are kind of new things. Yeah, but I give you also two papers here of these two people, Camilla Fabia with co-authors, also time fractional mean field games, so this possibly first papers, but they really consider this forward-backward system in somehow non-standard form. So they really have usual derivative, time derivative, and this fractional is somehow inserted inside the special derivative. So in a bit non-standard form, but they also consider this forward-backward system. Yeah, so again, I'm stressing that I will just speak like this. In this paper, we will speak only about the system, forward-backward system. And of course, in mean field games, the system are obtained as a limit of n players game. So this part will not be touched. This is somehow on our program. So to see how this forward-backward system really arises as a mean field limit of interacting n-player games, what are the corresponding arrow term, and so on. So, and another also general point, which I'd like to mention, somehow bypassing, so I also consider this as some reasonable contribution. We are going to introduce some general setting of Banach valued equations, which include somehow Mc-Kean-Vlasov and Hamilton-Jacobi-Bellman in somehow one setting. This makes it very simple, very convenient, I would say, because we often consider separately Mc-Kean-Vlasov, separately Hamilton-Jacobi equation, but in this framework, they are somehow in the same class. We just change the spaces where somehow the whole story develops, and then we can switch between Mc-Kean-Vlasov and the Hamilton-Jacobi equation. And there is also another general idea that if they are linked, as they should be linked for the mean field game situation, again, all the regularity on one of this equation, if you check it, then automatically by duality, you can check it for the second one. So just one check is sufficient. So these are general words, and now in more detail about this whole setting, but somehow the main point I have told already. Well, yes, so some plan about this abstract setting, as I mentioned, nonlinear fractional partial differential equations, including Hamilton-Jacobi-Bellman, Isaacs, Mc-Kean-Vlasov equation, fractional forward-backward system, and also something which I consider worth mentioning separately are this system on manifolds. I suppose that even in non-fractional setting, these things may be new. And also, if you ask, so who cares? Why do we need actually this forward-backward system on manifolds? Then I can say, well, these arise if you really consider quantum version of mean field games. So this is another pet kind of mine, which I'm not talking about today, but really these quantum mean field games, if you take these appropriate limits, then they will live on curvilinear spaces, on Riemannian manifolds, effectively in finite dimensional settings. They will live on complex projective space. So this is one of the ways to justify why do we need forward-backward system on manifolds. Well, abstract, I basically told you about abstract, so I will skip it. So this is somehow, well, the main guy, or so to say, one half of the main guy. Yeah, so as I say, we are aiming at a forward-backward system of this thing, but this is somehow the main equation. So derivative, usual, A is generator of some strongly continuous semigroup, usually Euler semigroup. And here you see a function, which I generally call Hamiltonian, which depends on the function and on some operator applied to this function, some unbounded operator, which you can have in mind as really a derivatives in all applications. This will be partial derivative. And then there is some parameter which depends on some, belongs to some other Banach-space. And effectively, we need it because in this forward-backward setting, instead of this alpha, we'll substitute some pieces of the second equation. So this is parameter which is needed to organize coupling. Okay, so this is usual one, but as I say, our main point, of course, is not in this one, but in its fractional version. So this is Jobarshan-Kaputa derivative, which already was mentioned several times in this conference. Order beta, and this A is the left side. So instead of the usual derivative, we take fractional. Also, well, this is a definition below, but I suppose it was already written here several times. Also, somehow general comments, which also I placed at the end by possibly say directly now, that here is really fixed beta. And this is not necessarily, in fact, there are very natural extensions. And in fact, I think that, in fact, for even mean field games, more appropriate would be considered this beta as a variable order. But this is some development which I will not properly have time to speak about, but just want to say that this is somehow starting point, this fixed beta in principle. We can have here generalized fractional derivatives, as also were mentioned several times here. But here, for simplicity, we talk about fixed time beta. Okay, so as I mentioned, Hamilton-Jacobi-Bellman and McKean-Vlasov, and I consider this an important point. It's nothing particularly remarkable, yeah, but this is very handy if you really look at this equation from one and the same point of view. So this is a fractional Hamilton-Jacobi-Bellman equation. So what is particular? Yeah, I mentioned there is Hamilton-Jacobi and there is McKean-Vlasov. They all depend on the derivative. Yeah, but in Hamilton-Jacobi, we usually assume that it depends on the particular value of unknown function. And in McKean-Vlasov, there will be some integral with respect to this f. But anyway, this is some dependence on the f, which makes this possibility to consider this thing together. Well, this is again usually how Hamilton-Jacobi, how the Hamiltonian appears in the optimal control, and everybody knows this formula. Not so important. I just want to stress that this fractional, the theory of this fractional Hamilton-Jacobi equation was developed by me with my former PhD students. So there is one of the reference. We have a couple of papers on this. So there are 2 points in this story. First of all, I suppose we were the first who really derived this equation. What I mean by deriving, I mean deriving as an optimal, as a kind of Bellman equation for the optimal control, which arises as a limit of continuous time random walk. So we can consider controlled continuous time random walk, their optimization as usual. And if we take the appropriate scaling limit, then that's the kind of equation which you can obtain here. Yeah? So somehow the one part of considering this as the limit of n particle system is somehow already done. Okay, and this is Mc-Kean-Vlasov. So in Mc-Kean-Vlasov, specific point is that actually the dependence on the gradient is linear. And yes, as I say, the dependence on function is not via a particular point, but as a general. Yeah, so in particular, you can think about here as kind of integral. And again, as I mentioned in the beginning, these are equations which are considered in Banach spaces, some abstract Banach spaces. But when we are talking, so here, when somehow the roots to Hamilton-Jacobi and Mc-Kean-Vlasov, when they somehow separate, they precisely separate in which Banach spaces it is convenient to consider them. When we consider Hamilton-Jacobi equation, you see it depends on particular points of the derivative. So very natural setting are point-wise estimates. And therefore, we are talking at the Banach spaces which arise from the spaces of continuously differentiable functions. So continuous, one time continuously differentiable, second time with this corresponding subnorm. When we're talking about the Mc-Kean-Vlasov equation, we have this integral term. Therefore, natural here Banach spaces are Banach spaces with integrable derivative. Well, derivative understood, of course, in the sense of generalized function. So therefore, Sobolev spaces and this L1 Sobolev spaces and W1 Sobolev space. So Sobolev spaces of function which has derivative of first or second order integrable in L1. Well, so this here I have written backward equation, possibly not much point to stay here, we'll just take in the opposite direction. It is important to write them, to have them in mind. I cannot completely avoid it. And usually one can say, okay, this is analogous. This is, of course, analogous. But once we are considering forward-backward system, then nothing to be done. One is forward, another is backward. Yeah. So this has to be taken into account. Okay, so very important for, well, as everybody knows that the linear equations, fractional linear equations are solved via the Mittag-Leffler functions. So I remind you these Mittag-Leffler functions, but important point for me is stress that we are interested, you see, in partial differential equation, where effectively this Mittag-Leffler function should be applied to an operator, to an unbounded operator. And of course, this definition is completely sort of senseless for an unbounded operator. Yeah? With infinite sum of Laplacian power. Yeah? So in order to do what we are doing here, we need some integral representation for this Mittag-Leffler function. And there are some versions of this. So in some Italian school, Mainardi, there are some representation via the curvilinear integrals. The representation which I find the most convenient is a formula which I call Zolotaryov-Pollard. There were some discussions, and it arises again and again. So where first this formula appears. So at least my understanding now that I read the paper of Pollard, that he said, well, the Mittag-Leffler function is a Laplace transform of something positive. But this something positive was not identified in his paper. It was later reproduced. It is actually later reproduced in the book of Feller already with reference to Pollard. But exact this thing was not there. But in the papers of Zolotaryov, it was exactly written in this way. So we see what is remarkably sort of great and convenient about this formula. Everything depending on this S sits in the exponent. So, and why exponent is important? Exponent appears when we talk about semigroup generated by something. Yeah. So imagine instead of S, you want an operator. So once you know exponent, once the operator generates some semigroup, then click, and the Mittag-Leffler function is defined. So that's the remarkable. And of course, it's very convenient that this is positive things. This tells us it's completely positive function and so on. Other important things. So there is G beta. This is actually comes from the, well, again, this formula already mentioned here in the previous talks. So this is a fundamental solution basically for the fractional derivative. Okay, so now there is again what is convenient to use. Of course, every well-posedness some one or another fixed point principle, so nothing to be done about. Yeah. So therefore, I remember that was remarkable. One of my papers was rejected by a referee who told me that the paper is trivial because it uses fixed point principle. I could not say anything, of course, against it. Yeah. But anyway, so this is the version of fixed point principle which I prefer mostly. And again, I would like to stress this. I prefer mostly in playing with fractional equation is a so-called Weisinger fixed point principle, which is somehow generalization of the Banach fixed point principle. Why it is convenient? It allows us to give the well-posedness directly for the whole interval. Yeah? So remember, if you go to school books on ordinary differential equation, then you say Banach fixed point principle for small interval, and then we iterate. Yeah, once you have fractional equation, you cannot do this. Yeah, you cannot just iterate because it keeps the whole memory. Therefore, this Weisinger principle is convenient because it gives you directly the solution for arbitrary finite time directly. Okay, and so this is somehow as a consequence of this Weisinger principle, I can formulate the fixed point principle with the following thing. We are interested in the functionals which go from continuous function to continuous function. And the point is that they do not depend on the future. And the difference is estimated. You see, this is like usual estimates for Gronau lemma, but here is the singularity. And this singularity, as long as omega between 0 and 1 is okay. I mean, we can still, from this inequality, we can still derive the existence of the fixed point. And if I look at this again, let me stress 2 points which I think worth being stressed. First of all, again, those who are playing a bit with fractional calculus, well, this is precisely the kernel which appears in fractional calculus. So there's something which you just automatically see. But what is not possibly so directly seen is that the same kind of thing we get even for usual diffusion. If you consider some Hamilton-Jacobi equation with the usual diffusion and write the fixed point principle, write mild solution, then again the singularity which you'll get will be of the same kind. With diffusion, this will be, of course, 1/2. Okay, so with these assumptions that the deviation of the functional depends on the deviation of the initial function, then we get, well, this fixed point principle, that this mapping has a fixed point, and we have explicit estimates also for the growth and for the deviation. And of course, again, those who are playing with this thing can imagine that all the estimates are given in terms of this queen of fractional calculus, in terms of this Mittag-Leffler function. So this kind of theorem, well, again, some estimates. This is particular case when omega is 0, not so important for us. Now, the assumptions. So the main tools for me to do with this thing is to consider triples, yeah, which can be called towers of Banach-space. Well, this is something like Gelfand triple, yeah, but here no Hilbert-space, but just Banach-space, quite sufficient. The main point is that the norm are ordered, and then B2 is dense in B1, B1 is dense in B. And why do we need them? So you can think about this B2 as kind of as a domain of the generator. So we're looking about, we will have semi-group in this B, for example, generated by this operator A. And B2 is kind of domain, and B1 some space in between, which allows us to do calculation. So effectively, we can think about this as continuous function. This is once continuously differentiable function. These are twice continuously differentiable functions. Or in the integral version, this is the same with corresponding Sobolev integral norms. So, and that's what we effectively need from our semi-group, this generated by the operator A. I remember this A is a generator which stays in our main equation, so that it will preserve, it will preserve as B1, B2, so B2 is kind of co-invariant core in this setting. Yeah. So these are these conditions which are written a bit more in detail here. So first of all, I wanted this operator D. Remember, the D is kind of derivative. So it continuously moves B1 to B, B2, B1. Again, the derivative, of course, is a continuous operator for continuously differentiable function just to continuous function, and so. So that's what is stressed here. And then, well, as A generates a strongly continuous semigroup, and that's important for me. That's not only in B, but in B1. So if we're saying about diffusion or stable-like process, not only B is invariant, not only continuous functions are invariant, but C1 functions are invariant, and we have the strong continuity there. Okay, so do not look very attentively at this slide. What is written here is Lipschitz continuity of these Hamiltonians. And it is written a bit messy because this Lipschitz constant usually depends linearly, yeah? Because you have, you can imagine if you have, say, linear dependence on the derivative, yeah, then if you consider Lipschitz continuity of the variable, then this dependence on the derivative remains. So the coefficient, Lipschitz coefficients, is not really uniform. It is linearly growing with something. And that's what is actually written here. Yeah? But the main point to have in mind that H is Lipschitz continuous with minimal as possible kind of dependence of the Lipschitz constant, which has to be linear in the variable, this B, which corresponds to the derivative. Yeah? And then this is another main assumption. This is smoothing. Yeah? So this A as a diffusion, if you consider the usual non-degenerate diffusion, yes, then the solution of the heat equation, diffusion equation, takes continuous function into continuously differentiable function. And of course, with some singularity, of course, at T0, yeah, we cannot just by click transfer continuous to continuously differential, but by some whatever small time you have, continuous functions are transformed to continuously differentiable function. So with for diffusions, this will be 1/2. For stable process or stable-like process or many other general processes, there will be, well, this alpha index 1/α when alpha is stability index. Well, so this is mild version. Everybody knows this. And this is the kind of theorem related to Hamilton-Jacobi equation without fractional term, which is not really important. So as again, this is somehow more or less standard thing. But this is the mild form of the fractional equation. Yeah, so there were lots of activity, some, I suppose, started about 10 years ago or something. So there were even some, I remember some erroneous papers who tried to write this mild version by analogy with. So you see, there is analogy with, but it's not exactly the same. So of course you have here Mittag-Leffler function, and here we have the derivative. So this is, but this is again for now already more or less a standard thing. But with this representation which I'm using, this Zolotaryov-Pollard, yeah, so this becomes the mild form. So what is here was looking at? Well, you see this operator A appears in the exponent. So once A generates a semigroup, then we have this mild form well defined. So this actually is the main point. And this, okay, this is some positive function for which you have some asymptotics and so on. And of course, here you have this Hamiltonian. So again, what's again like to stress here? You see what's going on. We want to consider this equation precisely in this B1, in this intermediate. Recall, we have this Banach tower, B2 belongs to B1, belongs to B. We want to consider this equation in B1, some intermediate thing. Yeah? So you have diffusion, twice continuously differential functions are core, semigroup is on continuous function. We want to consider the equation in once continuously differentiable function. Yeah, this is an important thing. And why we can do it? Yeah, because if what was going H, you see, H spoils the function. Yeah? And this A, because of the smoothing property, it reconstructs the derivative back. Yeah? So H spoils. Yeah? If we start with C1, it goes somehow to C, yeah? And then this thing pulls it back to C1. With the corresponding, of course, this will get this singularity minus omega. Well, so then the theorem, first theorem about this Hamilton-Jacobi, or basically Mc-Kean-Vlasov in this generalized Banach valued form. We have well-posedness, unique global solution for this mild version. So what one can add here, which is not here, is also you can get smooth dependence on initial conditions, smooth dependence on parameters. All is here in this rather general form, but I'm not mentioning here some details. Yeah, so, and again, let me stress these main examples. I mentioned them already, but again, let me stress them again. So if we consider Hamilton-Jacobi equation, then this is our triple. If we consider Mc-Kean-Vlasov, then this is our triple L1, and these are corresponding Sobolev spaces with integrable derivative of order J. Well, of course, these are the norm in these Sobolev spaces. I just reproduce them for convenience, that you can recognize here the familiar things. Okay, so then also some comments about the smoothing property. Remember, I stress this is important precisely to consider our Hamilton-Jacobi equation. Yeah? Hamiltonian spoils the function, semigroup somehow improves it back. So we really need this smoothing property. When do we have the smoothing property? Well, of course, we have it when A is non-degenerate diffusion, but we also have it when A is fractional Laplacian with any alpha between 1 and 2 here. And also more general, we can add some constant, and in fact, something even more general, which is somehow stable like or distributed Laplacian. So you effectively take delta in power alpha, and then you make a summation over some measure on the unit sphere. And of course, you can take even further thing. You can consider variable alpha, then the smoothing will be depend on maximum, minimum of this alpha, and so on. But for this case, omega is 1 over alpha. Okay, so this is somehow preparatory part. Yeah, so preparatory part was to be able to solve fractional generalized equation, which covers Hamilton-Jacobi and Mc-Kean-Vlasov. Now we want to put them together. Now we want this forward-backward coupled object. So in order to, so our general philosophy, which is of course quite natural if you start thinking about it. Yeah? If you have two equations, one forward, another backward. So the idea is let's solve the backward equation, then the solution substitute in the forward. Yeah? In this way, we reduce this system of two equations in one, but this one becomes more complicated because the coefficient of this one, in our equation, will depend on the future. And therefore, we consider now this anticipating equation. So equations with coefficients depending on the future. So you see, this is somehow as previously, and this is usual version with fractional derivative, Hamiltonian derivative B. And now you see, remember there was this parameter alpha. Now this parameter is, which we kind of are going to think as a control. And so this control will depend on B, but it will really depend on B in its future. Which destroys lots of course nice things which one can say and derive for the equation which depending only on the past. Yeah, but that's how we have to deal with it when we want to consider forward-backward system. And of course, we have this Lipschitz continuity. Well, this is standard Lipschitz continuity, but again, you see on the whole path now. Well, and then for anticipating equation, of course, we can write the same fixed point representations, the same mild form. So this is basically the same as previously, but again, you see what enters here. This is this unpleasant term. It depends on the future, unlike all this previous thing. And this is more explicit representation. So this is for usual case, and this is for fractional. Again, the same story. And now for this anticipating equation, we can get, by fixed point argument, we can get well-positiveness, but unfortunately only for some finite, well, small possibly time. Yeah? So this is the whole story, which again, well known to everybody who is working with mean field games. Usually, well-positiveness there in only for small times, if you do not assume some Lyon's kind monotonicity, which is a very special condition. But in general, we have multiple solutions. And if we want unique solution, which we are going to deal with here, is this really small time. Okay, and that's the theorem which tells us that we have this well-posedness for small time with this anticipating equation. Well, now forward, backward. So you see now we have the main point is as triples, but now we have triple for one equation, say for forward, and another triple for another equation. So therefore I'm saying, well, B2, B1, B, and this is B, this B means backward. Yeah. So we have triple for forward and we have triple for backward. Yeah? And again, to have in mind what we have in mind in application is precisely that this is triple of continuously differentiable function with subnorm, and these are integrable functions with integrable derivative. So we have this duality between these two things, which is really crucial for the whole application. Now our A and AB again, so they are operators in these triples. And again, I can say directly that for this application, AB will be just a joint operator, yeah, if we consider this. But in a more general setting, we just need this AB to be generator corresponding to this triple. Okay, so assumptions, again, do not look very attentively. This is again Lipschitz continuity with certain growth of coefficients of the Hamiltonian, similar to what was shown previously. Again, the same for this B means Hamiltonian for the backward system, more or less the same type. And now this is U, this crucial coefficients, which gives you this coupling. And of course, this U should be also Lipschitz with respect to this coefficient. Yeah, so again, I'm stressing that in this F, we're looking at forward-backward system. We're going to solve the backward equation, and solution will be substituted in the first forward. Yeah, and that's what we obtain this unified equation. Okay, so this is forward-backward written in this somehow in general form for the usual derivative. Yeah, so you see this B more than T indicates precisely this is the dependence on the future. And this is the link. So this we solve one equation, we substitute in the first. So that is the dependence which arises precisely in the mean field games. Well, and as I say, if we solve, as I will mention it, if we solve one equation, substitute in another, then we just obtained one equation, precisely the one which we considered previously, this anticipating equation. And if we solve it according to the previous theorem, then we also get the well-posedness for this forward-backward system, but of course, again, in small time only. Yeah, but what is more important is, of course, this fractional. So my stress is, of course, on fractional version. So this is backward. So this is fractional Hamilton-Jacobi-Bellman. This is kind of fractional Mc-Kean-Vlasov in a bit more general setting. And for them, we gain get the same story. We solve one equation, substitute into another, and then we obtain this one equation, but with this anticipating dependence. So this is solution of the previous depending on the first. And again, we have the well-positiveness of the thing for small times. Well, then some remarks also about this dual Banach triple. So I see somehow it was the main previously, possibly fact was the main result, some bit more particular kind of performances of this result. So here I really would like to stress a particular moment, which is important for mean-field games, when this AB generator for the backward equation is really dual operator for the A generator of semigroup in another equation. So here it is very convenient to consider what I'm calling Banach dual pair. So it's a pair of Banach spaces such that one is a closed subset of the dual of the respective other that separates the points. So this allows to consider B, B prime, and B prime B on equal setting, and even something more kind of general, like C infinity L1. Neither of them is a dual of another, but I nevertheless can naturally consider this forward-backward system in these two spaces. So they are not, one is not dual another, but they are dual pair in this sense. So in this dual pair, it is convenient to consider this forward-backward system. Now, another very natural notion, I say that this triple, and we actually used it already. I basically told about this intuitively. Now I'm saying that the triple is generated by this operator D, is the norm in B1 is norm B and sum of the norm of this DG, and the same B2 is B1 plus the norms of twice operating D. So you can consider again, this is B is continuous functions, B1 continuously differentiable. Of course, they are generated by saying B2 twice continuously differentiable, and they are generated by this norm. So these are very convenient somehow triple. So then if you use one norm in this like subnorm, then in other you consider this Sobolev space. Okay, and then DJ also, you remember initially they were just sum operator, but now we consider them as being dual. So this brings this more general setting into a more concrete one, which is appears. And now also some words about the smoothing property. So the smoothing property, you see, the main point was if you take continuous functions and move it by the solution of heat equation, then it becomes smooth and we can apply the derivative. But it's often convenient to use it in opposite direction. So first apply the derivative and then the semigroup, which in some sense does not make sense. What I'm saying, I'm taking continuous function. I am applying the derivative, but I cannot. But I say I'll do, and then I apply the semigroup. But in principle, it is still possible. This combination derivative and then apply the semigroup can be extended to a continuous operator, even though the first operator is somehow not defined at all. I cannot differentiate continuous function. But if I consider composition, differentiate, and semigroup, then this operator becomes well-defined. So this is another version of smoothings. Therefore, we have here smoothing from the left and from the right. And in this setting, it is very convenient because we're permanently jumping in this duality, so from one equation to another equation. So therefore, I'm saying smoothing from the right of the first order. So this is kind of usual smoothing. Apply, differentiate. And then it is convenient to consider smoothing from another side. So as I say, first differentiate, the semigroup. And here I'm saying first order means that continuous functions are transformed into continuously differentiable functions. And what is very convenient to use further is what I'm calling the smoothing of the second order, which means that continuously differentiable functions are moved to twice continuously differentiable functions. Okay, so this is from the right and from the left, as I say, smoothing of the second order. Yeah, a continuously differentiable function move to twice continuously differentiable function. And there are several properties of this thing, which I'm not going to be very precise about it. Well, there is just, I don't want to spend much time about it. So this is a particular version which tells a theorem which tell me when the required regularity for one equation can be transferred just by this duality automatically to required regularity of the second equation. And here you see this various connection of this right and left smoothing. Yeah? So smoothing for the first order from the right, then you see dual will be smoothing first order from the left, which is very natural, which this has appeared. Yeah? Smoothing from the right and from the left changes when we move from an operator and to its dual. And another thing which also very convenient for doing calculation, if we are able to consider the commutator of the semigroup and the derivative. So if we can prove that this commutator is a bounded operator, then all the smoothing from the right and from the left arises very naturally. Moreover, we have this direct link between smoothing from the right and from the left. And here we have result saying that this is somehow automatically equivalent for the operator A and its dual. And so these are not complicated kind of result by duality, integration by parts. Basically, you get this there, some other relations, but all these relations are important for really obtaining the results which I'm talking. Okay, so theorem forward. Well, yes, so this is now concrete forward-backward system for Mc-Kean-Vlasov and HJB. So I have written it as an abstract form. Now we having all these annotations, we can rewrite the corresponding equation in this general form. So now the last part of my talk, this is really which I stress at the beginning, that we can develop this whole story for manifolds. And again, I'm saying that I think, at least to my knowledge, that even for non-fractional version forward-backward system of this kind on manifolds were not considered. So even in this case, these are possibly new results. So if we consider, say, mean field games on manifolds. Yeah? So here remain some first possibly preliminaries, yeah, about the geometry. So this is a famous Laplace-Beltrami operator. Well, this is this expression in coordinates. Of course, G is the Riemannian metric. And now we are interested, of course, as usual, so heat equation. So this is heat equation on manifolds. And we are interested in the heat kernel, and there again, everybody, well, there are so many specialists like Remilian, there are many people. I don't know how many people work with this thing. So this is very well-known object, of course. Yeah, so this is heat kernel on manifolds, and everybody knows everything about it, basically. Now, what I'm interested in this smoothing property of the corresponding semigroup. So to formulate smoothing, we of course need to formulate proper norms. Well, with C is just sub, and if we're interested in the the first derivative, then we have to have here some invariant object, of course, to make sub. Well, an invariant object is, of course, can be written by usual lifting the matrix on the tangent and cotangent bundles. Okay, so this is norm first and then norm second. Again, this is invariant object, usual lifting of distance to a second order tensor. And the same with integral norm, which we need to consider dual Mc-Kean-Vlasov kind of equation. So again, you see we have the same triple. So this is subnorm, continuous function. These are integral norms, Mc-Kean-Sobolev norms. Okay, and so this is the theorem, which is not complicated. at least I looked for it quite a lot in the literature, but never found it. Yeah. So it's more or less kind of directly following from the property of the heat kernel, but still it requires certain work. Yeah? So this is smoothing property of heat equation on manifolds. So we have smoothing and smoothness preservation, and also what is important for me is that this commutator of the heat semigroup, and delta extends to a bounded operator. And also the same for this L1 and W1M norm. Well, and now once we have this, we can now move to this Hamilton-Jacobi or McKean-Vlasov equation on manifold. And here, instead of, that we had this general A generator, now as this A, we take a concretely Laplace-Beltrami on manifolds. Okay, and Hamiltonian, we can take again an usual form, which is used in optimal control. This is a function on cotangent bundle, of course. So this is our Hamilton-Jacobi equation on manifolds. Again, there is also a version with Isaacs equation, and we are going again to solve it via this mild form. So here, of course, again, let me stress that the theory of usual Hamilton-Jacobi equation on manifolds is, of course, studied by several people. Usual approach is, of course, via viscosity solution. So here my approach is it's simpler, of course, than viscosity solution, is mild solution, and it is meant to be written in such a way that I really more or less automatically can transfer it to the case of main interest, namely to the fractional equations. Yeah, so also this is possibly topic which is awaiting for the investigator, yeah, to properly look at the viscosity solution for this partial differential, fractional, and so on. And okay, and this is McKean-Vlasov on manifold. So again, we have the same A, and the dependence, some dependence, linear with respect to the gradient, and dependence on the whole F, which is usually again some integral with respect to, of course, Lebesgue volume on the manifold. Well, so this is a fractional version of this McKean-Vlasov of the manifold. So we have now everything. We have, and that we want to consider this forward-backward, backward fractional Hamilton-Jacobi on manifold, forward McKean-Vlasov on manifold, and of course our assumption, well, basically are done in such a way as to fit to the general theorem which was formulated, and this is kind of Lipschitz continuity, so that's what we're assuming here. Hamiltonian is a Lipschitz continuous function as usual. Then we have the well-poserness for the Cauchy problem for fractional Hamilton-Jacobi and for fractional McKean-Vlasov on manifolds as written previously. So there was for Hamilton-Jacobi equation. Now again, we in the McKean-Vlasov case, we assume this Lipschitz continuity of the dependence on F in McKean-Vlasov version. And then we consider finally, so this is somehow the main object of the final part. So this is forward-backward. So this is fractional Hamilton-Jacobi-Bellman on the manifold. This is forward McKean-Vlasov on the manifold. It is written in the form, again, with the assumptions done in such a way that can we apply the general theorem which was formulated, well, assuming, again, usual Lipschitz continuity there and there, assuming this Lipschitz continuity. Again, H should be continuous. So I basically reproduce the assumption which were written previously in this somehow concrete version. And well, we have the existence of the solution of this forward-backward system. Okay, so two things which I again, I started with these two things, and I'd like to stress them again, because I consider this really as is crucial for further development. So first of all, my understanding of this, what one naturally should consider in a mean field limit of interacting particle, I think the very natural is to consider really variable order derivative. Why variable order? Because when we are modeling interacting particle in usual our exponential way, then the intensity of jumps of interacting particle in certain states, they depend on the state, because this is really, the intensity is given by this Levy kernel. Therefore, effectively, when we have several particles in several positions, then the waiting time is realized as a minimum of this exponential time, which is again exponential time. Now, if we consider the same when waiting times in our continuous time random walk approximation, which are not exponential but polynomial, now if we take the minimum, then there will be again power decay, but with index, which is a sum of the indices of each part. So this will be position dependent, most natural way. So I think in the most natural way, really, the equation which I have written to be really appropriate for mean field games, they should be really extended to this variable order version. Okay, and then the second thing, of course, which again waits to be given is this forward backward system. Okay, this is the limiting mean field games, but the crucial question, of course, as always, is how does this thing approximate this continuous time random walk kind of approximation of a finite number of players? So this is left to be analyzed, but I think that all the machinery which is done here already allows to make a conjecture that basically we will have the same rate of convergence, that we will be able to show that that the solution to this limiting forward backward system gives you in fact this epsilon n approximate Nash equilibrium for the corresponding system of n players with this epsilon n estimate, which can be 1 over n in case of everything sort of very, very smooth, and 1 over n in some hour power, like was sort of mentioned in previous lectures, if we have not such a smooth thing. So yeah, that's the main thing I wanted to say. Stop now. Thank you for your attention.
Thank you very much for your interesting talk with a lot of facts and theorems. And there we have 5 minutes for questions. Of course, I cannot see people from the audience, so if you have questions, please ask.
Rika.
If there is no question, I have 5 minutes. Okay, I think
No.
Okay, now it should work. So, I guess Laplace-Beltrami operator emerges as a semi-group generator of a Brownian motion on manifolds. So, similarly, is there the possibility of having generalization to sort of alpha stable motions, for instance, on manifolds? Or
well, this is very natural questions, and I think this is possible. Yeah. So instead of Laplace-Beltrami, you can consider the fractional power of Laplace-Beltrami. I'm pretty sure that we also have this smoothing property, but I didn't check it. But this is really worth being checked. So we consider really stable like on manifolds, which is not such an obvious object. And then we have some discussions. So with Astrid, what one can in fact have several approaches to what is alpha stable on manifolds. So the simple thing, of course, we just take this fractional power Laplacian, but maybe this is not really exactly the same. which would be meant if we try to generalize somehow Levy-Hinchen formula, which is not very clearly defined on the manifold. So this is very interesting and nice way to think further. Yeah, for the moment, nothing is done in this direction.
But for some manifold like sphere, there is a very nice solution of the eigenvalue problems in terms of spherical harmonics.
Yeah, sure.
This gives you a new opportunity.
Yeah, in particular, yes. If you have some symmetry, this gives you.
As far as I know, it's again have some eigenvalue problem is solved, which is
Yes.
as far as I know.
Yeah.
So I think that at least for a sphere, you can give much
Sure.
more detail.
Sure. Yeah, so as I say, for say quantum games, so the very natural manifolds are complex projective space or the infinite dimensional version, so which is also something of interest here.
So there is something in the chat.
No, I just checked that there was nothing, but it could still be. Maybe
But
just
if you,
talking to the virtual audience also, please unmute or raise your hand if you have questions. Wait a minute.
but even more, I mean, there are so-called spin spherical harmonics. I mean, if you consider some sort of, well, I mean, I'm not sure, but I mean, this can be extended in the context of the spherical harmonics,
Yes.
spherical harmonics, which naturally appear. And
Sure.
your
It's
solution of eigenvalue problems, this gives you forward.
yes. Sure. Yeah. And of course, you can use this expansion to get the smoothing properties. It all comes out.
Fractional power of spin spherical harmonics.
Yeah.
I mean, Laplacian, fractional power of Laplacian.
Yes. So corresponding eigenvalues will be just in powers.
Not Laplacian, but some sort of operators which are related to.
Yeah.
I don't know. I mean, this exists.
Yeah. Sure. Yeah. So very much welcome for Hamilton-Jacobi, McKean-Vlasov on manifolds. Suppose many things to be done here, to think about it. And also, as I say, in particular, in the direction of viscosity, because I've seen the paper on viscosity for Hamilton-Jacobi, but fractional or forward-backward. So it's a very, very nice direction to think about.
Yes, thank you for the talk. But I'm a little bit behind with the concept of backward, just the backward part, because this is a mixture of pathwise and stochastic calculus in some way. So this, in this existence part, there is always this Martingale representation type results that are characterizing the solution of the backward. And here it's an anticipating context and also a different kind of calculus. So what is the, I've lost the feeling of the solution somehow.
Okay, thank you for your question. So I think the reason for your question is my using of word anticipating. So everybody is used to this word in probability, but in this sense, it has nothing to do with probability. I mean anticipating just depending on the future. So we have no stochastic equations here. Yeah? So Hamilton-Jacobi equation is just deterministic, and the McKean-Vlasov just deterministic. So it's nothing about martingale or whatever. If they arise, of course, as optimal control solution for diffusion control, fine, yeah. But once they are written, yeah, they are written as deterministic equations. So no question here arises about backwards Hamilton-Jacobi equation. If you write. Consider control diffusion, just usual control diffusion, forget about manifold. Control diffusion, which I here am controlling, is only drift. So if you write Hamilton-Jacobi, which is effectively Bellman equation for the control diffusion, then you, of course, get it in backward time because you know what at the end. Yeah. So, but this is deterministic equation. So, yes, yeah. Yes, of course, you can do it by stochastic, but what I'm saying, what you can do it, but I'm not doing it in a stochastic way. I'm doing it in a deterministic way, which avoid this complicates the thing. Yes, of course, if you want to do it stochastically, follow by paths, again, the whole world here. And of course, you will deal it with some backward stochastic differential equation, which I mean, fine, but this is just different story. And this is, okay, something again worth looking about, yeah. This Pontryagin maximum principle, backward equation, but this was not in this. This was not in this talk. But this would be, of course, interesting to look at this in this, as you say, as a process. So it's a very natural suggestion what one can do here further on. Sure.
Is there any question more? Yeah. I checked the virtual audience, and there was no question either. So, well, where is our chairperson?
Chair disappeared.
Yes, okay. Mhm.
Oh, chair appeared back.
Yes. So, okay, so thank you very much once again for your talk. And now we have the next speaker. Yes, the next speaker is Professor Dorota Muzyrska from Białystok University of Technology. And the title of her talk